doing, let's see, we did 1 degree of freedom, let's do one more. Salad greens are being washed. Dirt, bugs, and debris come with those greens out of the field, and we need to wash them and package them for sale. Greens, salad greens are mixed with 150 gallons of water per day and washed, then spun to separate the dirty water. The process removes 99.9% of the dirt, bugs, and debris, and all of the water from the greens. Then they get packaged. The dirty water goes to the river. The plant can only dump 4 barrels of water a day and only 1.5% dirt, bugs, and debris. And then the question, is this problem completely specified? That's what tells you this is degrees of freedom. You don't have to solve the numbers, we just have to check, is it solvable? Okay.
There's 2 streams going in, water.
All right, what do we do first for degrees of freedom? We draw a picture, right? Why don't you draw a picture? 30 seconds, draw a picture, see what you got, check with your neighbor.
Water and dirty greens. And it's a mixer.
It's a mixer.
Yeah. And then there's 1 stream coming out. And that has everything in it, and it goes into a separator.
Then?
And then you have a stream of dirty water and dirty greens.
Water, clean greens. Great. Thank you. All right, then we need some variables, right? Or we need to label this. Choose some components and label them. What should our components be? And dirt. Okay, so this is an example of using composites instead of molecules or atoms. So let's have some greens. Let's have some dirt. Let's have some water. So here we'll have greens, dirt, and water. And then the output stream, let's see, said dirt and water. What comes out here? Greens and dirt, right? Okay. Super. Label the flow components. Show any components in each stream and accumulation. Do we have any accumulation in the system? No, so why do we know this is steady state? What kind of process is it? Continuous process, not batch, not semi-batch. So stuff's moving through on a per day basis. This thing is just regularly going. So yeah. So that's our clue that this is a steady state process. Actually, it could be a batch. It could be one big batch for the day gets run. But anyways, at the end of the day, there's nothing left in the mixer. There's nothing left in the separator. Everything's moving through at a steady state. Okay, so no accumulations. Write down any chemical reactions. None. Okay, so the degrees of freedom. Count the number of independent variables. Step 4, variables. So first we need stream variables. Let's see, we can just count these. We could also label these. Stream 1, stream 2. Step 1, choose a system. What should we choose for a system? Mixer, separator, or both. That's our choices. Everybody's saying both. Okay, so I think this is the first time we've done this with multiple units. So we can pick our system wherever we want, and we can do an analysis. We could do one unit or the other unit or the total unit. So if we do that, this stream in the middle kind of disappears. It's inside the system, it doesn't cross the boundary. The streams we care about are the ones that cross the boundaries. Okay, so that's a pretty key step for this. What that does is then I don't have to count these variables in the inside, and we can solve the whole overall process. Okay, so I'm going to call this stream 1, stream 2, stream 3, so that's dirt 3, water 3, stream 4, greens and dirt. Okay, then and my stream variables, how many are there? G1, D1, W2, T3, W3, G3, and D3. 1, 2, 3, 4, 5, 6, 7. 7 stream variables. B. System variables. How many system variables? Anybody see any? Okay, no system variables. No accumulation, no reaction, so we don't have any system variables. Great, that's variables, equations. A, specified flows. Actually, let's see, so we'll do flows. B, stream composition specs. C, system performance specs. And D, material balances. Take 2 minutes. Write down as many specs as you can see. Do it in your small groups, 2 or 3 people. Put them into those categories, see what you got. What do you have for specified flows?
150 gallons per day is one.
150 gallons per day is going to tell you which stream.
W2.
W2. Okay, so W2 equals something like, I don't know how we do this, 150 gallons per day. Those aren't the right units, they have to be converted, but just for now we know we can get there from there. Okay, great, that's one.
G1 equals 1,500 packages per day, or would that be G1 plus D1?
1,500 packages of greens per day. Yeah, where are those packages?
Oh, that's just G1, and then D1 is 1 pound per 12 pound greens.
Okay, let's hang on to the 1 pound per 12. Let's go back to the 1,500. So where is that 1,500 pounds? Which stream is that? So you're saying that's G1. Mm-hmm. You're close. So the packages per day, you want to help check?
It's output, so it'd be G4.
That's everything. So 1,500. That's our output. It's actually not just G4.
Oh, it's G4 and
What's in that package? You measure a whole pound in the package. There's a whole pound. 1,500 pounds is G4 plus D4. It's the whole stream. Pounds per day. Yeah, that whole thing weighs a pound. That includes the dirt. Questions? Any more specified flows? Okay, how about stream composition? Molly, you have any stream compositions?
I have a question. Is it
Yeah.
like 1,500 packages?
So 16, okay, I did some conversion. 16 ounces is 1 pound. So that's 1,500 pounds. Yeah, so this will go down to packaging, this will go to packaging, and then you'll get actual mini boxes of packaging. Is really just a splitter to put it in a bunch of.
So for the stream specification, I think we should be 1 pound So my equation is E1 over D1 plus G1 equals to 1 over
Say.
D1 over G1 plus D1.
I think I would count this as D1 over G1. The dirt to the greens. Let's see, 1 pound per 12 pound of greens. Yeah, let's see. That one, I think I would count. Okay, so I told you that last one, I count greens as the whole thing, including the dirt. But this one, because we're talking about the ratio of the dirt to the greens, I 1 to 12 pounds. I think that's what I would do with that one. 12 pounds of green, 1 pound fresh picked green, 1 pound per 12. Yeah, it's a little bit ambiguous, so I might ask for clarification. Is that 12 pounds of the greens or 12 pounds of just the leaves? I want to say it's 1 to 12 here. Otherwise, it's 1 to 11. You're just going to take out 1 pound of dirt. Okay, any more compositions? 4 barrels of water per day. 3. What do you think? Should we include that or not? Equals D3 plus W3. Somewhere in there with units. I don't know, that's got some units things. What do you think, Joanne?
Would that be under system performance, because this is the plan that's loaded as well?
Is it system performance? Let's see. System performance would usually be talking about how much you're actually separating, whereas this is a whole flow. So no, I wouldn't put it under system performance. I put it under flow if I'm not doing it at all. Victor? Specified flows? Yeah, Jack?
I wouldn't include it because it says that's a maximum dumping. But I just looked at the conversions and 1 barrel is 42 gallons. So 4 barrels is more than their input of water anyways.
Is that right?
Yeah. So that's saying it's the maximum, but they're putting in less water, so they can't take out the maximum. So
But they're also getting up dirt.
Did you say they're putting in less water or more water?
they're putting in less water.
Less water.
So that's just saying it's a
You
maximum.
think you're already under the limit?
Yeah.
Other
I
thoughts?
just wouldn't include it because you have to choose one of the two as a basis, because if you already know how much dirt, grains of water, and then it can't, it's gonna equal the
That
output.
kind of seems redundant with this with W2. Okay, so it's a maximum. It's not exactly what you have, so let's treat this one kind of special. Let's write it down. So one thing you can do with limits, say if you have an environmental, well, let's talk about, we can talk about the other one. If you have an environmental limit, a lot of times you want to run right at that limit because that's how much you're allowed to do, and you want to maximize production, so a lot of times you go with that limit, and you just set that as your flow, or maybe a little bit below for some safety and some margin for error. A lot of times you just set that and you'll use that equation. Other times, as long as you're under it, it doesn't matter. So maybe you don't need this, or maybe you can use this. So this is where you actually have a little bit of flexibility in your design process if you're making this design. It's either going to tell you your design's no good, your design's plenty good, or maybe you have a degree of freedom and you can use this as a spec to go up to maximize something else in your design, like profit or minimize environmental damage or something like that. Okay, what else? Let's do system performance specs. Troy.
Separator has to separate 99.9% of dirt from the salad greens.
Separator's got to get 99.9% out, so give me an equation for that.
Okay. D3, the dirt coming out is 99.9%, the dirt coming in, or D1.
D3 over D1's got to be 99.9%. Yeah, so a good way to see this is stuff going in and stuff going out. That's through the system. That's a system performance spec. Yeah, okay. Any other system performance specs? Did I miss anything?
For stream composition specs, if we're taking the barrels, then we should probably take the DVD content.
Okay. DVD content. 1.5%. What's the equation for that? What do I do with that?
That was D3, right?
D3.
And D3 plus W3.
D3 plus W3. Okay, and this again is a maximum. So I could use it, or as long as we're under it, it's fine. It's either going to be a go, no-go, or we can use it if we need it. Okay, so stream composition specs, let's go with 2 there. System specs 1. Stream, okay. Great, material balances. How many material balances? It's the rule. I get 1 for each component, so I've got greens, dirt, water. That's going to give me 3.
Also, aren't there just 2 specified flows?
Not 2. let's see, water flow rate was given, greens flow rate was given. Right, so this one, if I add in the barrels per day, that's the fourth, that's the third. Okay, so 3, 4, 5, 6, 7, 8, 9. This gives me 9 equations. So what do I have for degrees of freedom? Troy?
No, just a question. How does barrels per day equal to a flow rate? Because that's just a limit, isn't it?
Okay, so yeah, so if we want to run at the limit, we could set it as an equation and use it as an equation to specify our system. So what do we have for degrees of freedom?
-2.
-2. What's that mean?
Some things redundant.
What's the word, the term for overspecified? We have too many equations. So now, put those limits into context. If we actually set 4 barrels a day coming out, and we set 1.5, we have too many things specified. So that means we have too many constraints in the system. So what we want to do is not use these as equations. If I take these out, then I would go back down to 7, right? So let's actually make this 1, let's make that 2. That'll make 7 equations, 7 unknowns. I can solve the system without those limits, and then we can see, are we above the limit, are we below the limit? Okay, adipic acid from glucose. Adipic acid, C6H10O4, AA, is a building block molecule for nylon. Everybody knows nylon. It's polymer in lots of synthetic clothing and other plastics. Although traditionally made from benzene from petroleum, so we usually make nylon from petroleum, a new route has been proposed to synthesize adipic acid in a bioreactor using E. coli being bacteria. The bacteria will turn the glucose into gluconic acid, C6H6O4. And there's the reaction. Subsequently, the gluconic acid is hydrogenated to adipic acid. So we take the C6H6O4 and hydrogen gets C6H10O4. First thing we need to do, step 1 on degrees of freedom or solving process calculations, is sketch a block diagram for the new process. Can you design, what blocks would you need to make this stuff? All right, where would you start? What do we need to make this stuff? Troy?
I just have to say the second equation isn't balanced quite correctly.
Second equation's not balanced.
Not quite. You just need a 2 on H2.
We need 2 H2s, thank you. So first one balanced? Looks like it's supposed to be.
Yeah.
It's not.
Cool, thanks. All right, so how do we sketch a block diagram? So this is kind of your open-ended, if you were working for DuPont and they said, hey, we have a new process, let's see if we can sketch it up, design it, see if it's profitable, see if it's going to be more environmental than going to the fossil fuels. This is where you do. You start and say, this is the idea. So where do you start? Synthesizing block diagrams. So Murphy has some rules for doing this. She says, step 1, start with the reactors. That's the heart of your process. How many reactors do you need for this process? 2. Reactor 1, somewhere down the line, reactor 2. Step 2, mixers before the reactors. What do we have to mix in these reactors? First reactor needs what? Glucose. And E. coli. What else? Oxygen. So mixture number 1, I want to get glucose and oxygen in. And And the E. coli, actually, we're just going to stick in this reactor. This is going to be actually a fermenter. Same thing you use to make beer or yogurt or anything with a biological process. So we'll have E. coli living in the reactor. We'll mix glucose and oxygen and feed those to the reactor. What's going to come out? All those products, metonic acid, and CO2, and H2O. E. coli are actually going to come out too, because the E. coli grow and multiply and split, so we're always going to have those coming out of the reactor. And we might have some of the products going into glucose and oxygen. Okay, second reactor, gluconic acid and hydrogen, so we're going to have to mix before this one. Next two we'll have hydrogen, and we'll have gluconic acid. Let's see, step 3. Consider separators before reactors if the feed is not pure. So the air going in is not pure oxygen. We could consider a separator, separate the oxygen and nitrogen and feed pure oxygen. There may be processes we want to do that if we've got a lot of substitution reactions going on. We don't want amines getting in there. We don't want the nitrogen to get in there. It's probably going to be pretty expensive. So in this case, we probably don't want to separate out the nitrogen. Add separators after the reactors. So we want to separate our desired components from our undesired components. So in this case, let's see, there are some liquids we want to pull off with E. coli and water. There are some gases we want to pull off, CO2, nitrogen, maybe oxygen if there's extra oxygen. And then the main thing we want to get out of our separator is the muconic acid. And the muconic acid, then we can connect somewhere through here if I had it. Okay, and then the second one, second reactor, out of that comes adipic acid, maybe some leftover muconic acid, maybe some leftover hydrogen, and I want to separate that out too. Adipic acid, hydrogen, and muconic acid. Step 5, do splitters if the quality is too high. If you've got too high a quality and you don't need that high quality, you might just split it, take some of your product and some of your reactants. It's much cheaper to split than to separate. Step 6, recycle unreacted reactants. So as hydrogen and muconic acid, we might want to bring back to that mixer, which is one reason why it's good to have a mixer out front, because then we can explicitly put these recycle streams in. Let's see, CO2, nitrogen, oxygen. We don't really need to recycle oxygen because we can get air. E. coli, they're going to be making more all the time, so we don't need that. And the water too is products, so we don't need to recycle those. Murphy has some heuristics on this, and maybe I'll let you read these. You can do this different ways. These are just some rules of thumb. She thinks you should mix the raw materials as late as possible, maybe even just before the reactor, so you don't get any side reactions. Separate byproducts and waste as soon as possible, meaning just after the reactor. If possible, split rather than separate. It's cheaper. If possible, mix streams together of similar composition. It doesn't actually, mixing air and glucose solution, they're two different phases. One's liquid and one's gas, so this doesn't even make too much sense. You're right, we might just want to put that in the reactor. Okay. From there, once we've got a process, then we can ask the questions. Determine